Okay, so how's everyone today? Good? All right. So we've been talking about equations. We still got lots and lots to say about that. Here's an interesting thing concerning the reals. We can say let A and B be in the reals. Okay, then A multiplied B equals 0. That statement, it implies that A is 0 or B is 0. Or both, right? And so all that's saying is that if you're multiplying stuff together, and we just wrote 2 factors down, but it can be 2 or more factors. If you're multiplying stuff together, and one of the factors is 0, then it doesn't matter what the other factors are, the result's 0. So like if we want to multiply, like 8 multiplied by 10, multiplied by 13.7, multiplied by 0, multiplied by pi, multiplied by whatever, well, what's the answer? 0, right? So it's all that this is saying is that when you multiply stuff together, if the result is 0, then at least one of the factors is 0. All right. Curious. So that's sort of an obvious thing, when you say it that way. But the way we're going to use it is we're going to use it to solve an equation. To solve an equation in the following kind of way is that notice that we've got sort of 3 equations here, and I'm going to say that this is like the big equation. So there's like one big equation, and we'll be able to break it into two smaller equations. All right. So that's going to be the idea. So here's the exercise. So please solve. W squared minus 17w plus 60 equal 0. Okay. So as a reminder of what that means, that means find all w such that the equation is true for that w. So, for example, if we just wanted to sort of blindly guess, we could sort of just guess like, well, what if we plug in 10? We'll just plug it in and just see what happens. Hope for the best. Okay, so if we plug in 10, then the equation reads 10 squared minus 17 times 10 plus 60 is equal to 0. So then that would read 100 minus 170 plus 60 is 0. And then, just adding, you get negative 10 equal 0. So is that an equation? Yes. It's an equation. What's its value? False. So its value is false. So don't be misled, right? That is an equation. Its value is false. Okay. So that means we can conclude something about W is 10. It means it's not in the solution. All right. So therefore, W equal to 10 is not in the solution. and again, by way of maybe just guessing, we could guess, well, what about, say, W is 5? What if we plug in W is 5? All right. Then we'd get, 5 squared minus 17 times 5 plus 60 is 0. All right. So then that would be 25 subtract 50, 35, 85 plus 60 is 0. And then, you do the arithmetic there, and you get 0 equal 0. So how about that? Well, that's true. So what does that tell us about W is 5? It's in the solution. Okay. So I'm just reminding you of stuff. Okay, so this actually isn't a work towards solving the problem. I'm just reminding you what this was about. So, we know that 10 is not in the solution, and we know that 5 is in the solution. But the point of the exercise is for you to find all the W that are in the solution, and therefore you also know all the W that aren't. So, there's infinitely many real numbers, and in some sense you could say, well, we've checked 2 off of the list. Infinitely many more to go, right? Okay. Fine. So rather than trying to check them all off the list, here's what I'd like you to observe. Is that we can take that equation, W squared minus 17, W plus 60 equals 0. And then now notice that the left-hand side is a monic quadratic. So that's like one of our favorite things. We dealt with monic quadratics for like 2 weeks in a row, So does the left-hand side factor nicely? Yeah. How does it factor? Yeah. We have W minus 5 multiplied by W minus 12 equals 0. So that's nice. And now that you have it factored, do you see that? Oh yeah, when we checked W as 5, we determined that it's true. Well, do you observe that concerning these two factors? If you plug W as 5 into that one, what would that factor be? It'd be 0, right? So it's kind of obvious now that we did that, isn't it? So here's the point, is that now here's where we're finally going to use this observation about the reals. So what we're saying is, like, this is a big equation, and this is, we factored it, but it's still kind of a big equation. And what this is saying is actually we can break it into 2 smaller equations. We can say that there's actually 2 possibilities. Because we have the product, this product is 0, that means that either that factor is 0 or that factor is 0. So it's saying that W minus 5 is 0, or W minus 12 is 0. So observe what we achieved. We said that we were asked to solve this equation. And then we did a little bit of factoring, and we said that, hey, look, we can actually break this one big equation into 2 smaller equations. So now we have twice as many equations. That's bad. But they're, the ones that we have, they're a lot easier. That's good. So, this one's pretty easy. How do you solve it? Yeah. So W is 5, and then similar for this one. W is 12. Okay. So the conclusion of this work is it's saying that there are exactly 2 W's that you can plug into that equation so that you'll get true. You can plug in 5, and the result will be true. and you can plug in 12, and the result will be true. And if you plug in any other w whatsoever, the result will be false. So if we plot this, so this is saying, the solution is the set 5 and 12. So those are curly parentheses. The proper name for them is braces. So if we plot the reals here, then we've done plenty of plotting on the reals, but most of the time it's been intervals. But this is not intervals, rather we're just plotting individual points. So there's just 2 points. There's this one and this one. So that's the solution. And now, to make sure that you understand the connection between the solution and the plot. So, we did this algebraic maneuver here using this observation. Break one big equation into 2 smaller equations. And we got 5 and 12. But, here I asked about 10. I asked about W's 10. And, there's not like a scale here, but 10's about right there-ish. Oops. 10's about right there. And I asked, is 10 in the solution? Or alternatively, what will the equation be false or true when you plug in 10? It'll be false. Okay. What about like this point right here? This might be like, I don't know, this might be like 28. What will we get if we plug in 28? False. What do we get if we plug in 5? True. So what's the connection? It's kind of, I'm trying not to hit it too hard. But, the connection is that concerning this equation, the solution is the set of all points that when you plug in, you get true. And the plot is that we have painted every point such that the equation would be true there. And every point that's not painted, the equation is false. So the equation is false for all of those, it's false for all those, false for all those. Those are the only 2 points where the equation is true. Any question about it? All right. So that's the case for an equation in one variable. So now, let's consider an equation in 2 variables. So consider something like y plus 3 is equal to x minus 2. No, not that. Sorry, I want to say y plus 4 is x minus 1, and then square that. Okay, so it's an equation. There's 2 variables, x and y. All right, fine. First request, solve for y. What I mean is I want you to take that equation and I want you to get it in the a form that looks like this. Y equal blah, blah, blah. So this is not like a trick question. It's pretty straightforward. Yeah, subtract 4. Okay, so then y is x minus 1, square that, subtract 4. So notice that, we have, this equation and that equation, they're equivalent because what we did a move that's completely legal. It's always fine to add or subtract 4 from both sides. It won't change it. Okay, so now 2. Would you please fill in the following table? So we'll start at -3. So -3, -2, -1, 0, 1, 2, 3. We'll go to 5, 4. 5. So what I'm asking for you to do is that I left all the y's blank, and for each one of those blanks, I want you to take the equation and replace the x with the corresponding value, and then tell me what y would be. So, like, for example, for this one, I'm saying that take the equation and replace the x with -3, so that you'd get y is -3, subtract 1, square it, subtract 4, and then carry out that arithmetic. 14. So let's see, that would be -3 minus 1, no, not 14. So it'd be -3 minus 1 squared, so that'd be -4 squared, and then subtract 4. So it'd be 12, right? Because it'd be 16 minus 4, so it's 12. All right, 12. So you can imagine, filling it all out. So in the interest of time, I'll just do it quick here. So -2, -3, 9 minus 4. This would be 5. -1, 2. Really? Wait. -2. No, it won't be 0, will it? Because -1 minus 1, that'd be -2 squared would be 4, minus 4 would be 0. Yeah, okay, 0. Brain is just gone. So then, what would this be? 1 minus 4 is -3. And then this would be -4. Okay, interesting. Now, from here, because because I've taken this class before, I know that there's going to be a neat pattern going on. So in fact, I'm not going to have to evaluate anymore, because I know that that there's going to be a neat symmetry here. This one's going to have to be -3, because that one is. This one's going to have to be 0, because that one is. This one's going to have to be 5, and this one's going to have to be 12. So note that the red numbers there, they read the same going forwards and backwards. So when that happens, that's called a palindrome. So examples is like the word race car is spelled the same forwards and backwards. That's interesting. Okay, fine. Now I'm going to do left column and right column. So 3, would you please evaluate at the following points? Evaluate. So at xy is 4, 5. So do that, and also please evaluate at xy is 2, 1. So evaluate the equation. So, in the end, what I'm asking is for you to take that equation and then, replace all the xy. So replace all the x's with 4 and replace all the y's with 5. Okay. So it would read, yeah, eventually. So 5 equal to 4 minus 1, square that, subtract 4. So that would be 5 equal to 4 minus 1, that'd be 3 squared is 9, so that'd be 9 minus 4. So that would read 5 equal 5, which is true. Okay, good. And as for this, the equation would read, so 1 equal to 2 minus 1, square that, subtract 4. So 1 equal to 1 squared, so that'd be 1, subtract 4. So 1 equal -3. All right, how about that? False. Right? Okay, good. So just like on the previous page, when we were dealing with an equation in one variable, we could plug in values. Apparently some of the time we get true, and apparently some of the time we get false. And what we're going to be interested in, is the set of all points where you, when you plug in, you get true. So, you know, I knew I was going to get true for this one. The reason why I knew I was going to get true for this one is because I read it off of the table. Right? XY is 4, 5. So I knew we were going to get true. And, you know, I wanted this one to be false, so I just looked up there and looked at and saw, well, 2, -3 would be true. So I just wrote 2 and then anything except -3. So we'd get false. Okay. Curious. But now what we're going to do is we're going to plot the points on the table. So if we plot all those points, let's see how it'll look. So notice that it's a, you know, we mentioned that it's a palindrome. So I'm going to plot the middle first. So 1, -4. So 1, -4 is right there. And then I'm going to plot going to the right. So so 2, -3. So 2, -3 right there. And then 3, 0 there. And then 4, 5, 4, and then 1, 2, 3, 4, 5, and then 5, 12 is way off, so I can't, you know, I can't go that high. Now the fact that it's a palindrome means that the points are going to have a nice pattern. It's going to make a nice looking shape. So that's the middle of the palindrome on the table. That point. And then going the other way, that means that corresponding to this point is going to be that point. So those two correspond to each other. And then corresponding to that point is going to be this point. And then corresponding to that point is going to be this point. Interesting. So we plotted 7 points. So that's neat. And now, because this equation is sort of, you know, a nice equation, we could get a better idea of exactly what the picture should look like if we just kept plotting more and more and more points. But because this equation is a nice equation, we can more or less get the right idea by just connecting the dots smoothly. So I'll do that. It's going to look something like that. Okay. Curious. So that's a neat looking shape. So that's going to be a really important shape for us. So I'll go ahead and tell you the name of that shape right now. So the name of that shape, it's called a parabola. Parabola. It's important in math and science and things like that. In engineering, a typical example would be something like satellite dishes. The dish part of it is that shape is parabolic. The reason for that is because such a surface, when photons come and hit it, they bounce off and reflect, and all the reflections are sort of shepherded into a single place that can be focused. So that's what a satellite dish is. We've kind of got like satellite dishes on the sides of our heads here. That's what they are. They're not shaped like parabolas, but they do the same purpose. Fine. Curious. Now, what's the connection? So, all right. Over here, I asked you to evaluate 2 points. I said, please evaluate 4, 5. Evaluate the equation at 4, 5, and please evaluate the equation at 2, 1. So let's figure out where is 4, 5. So where is 4, 5 on the plot? Well, it's right there, isn't it? That's the point 4, 5. And where's the point 2, 1? Yeah, it's about right there-ish. And so what we said is that, well, when you plug in 4, 5, the equation is true. And when you plug in 2, 1, the equation is false. All right? Now here's some point, and I'm not pointing exactly somewhere. I'm not on one of the grid lines. I just chose some point. But if we were to carefully get out a ruler and figure out where I'm actually pointing at, and then if we were to plug it into the equation, what would the result be? False. Okay. What about this one? It'd be true. It'd be true. So what's the connection? What's the significance? The connection is this: is that the meaning of this drawing is that we're saying that concerning this equation, some of the times, some points that you plug in, the result will be false. Sometimes the points you plug in, the result will be true. What this picture is, this is a picture of all the points, such that when you plug them in, you get true. So concerning this equation, right? False, all over here, false, 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 true, like that. Okay, so the set of all points for which the equation is true is called. Now, if I had my way, the name that I'm about to write down, I would write the same thing that we did here. Is that this in the case of finding the set of all points such that this equation is true, we named that set the solution. So that's what we called it. So it seems to me that concerning this, we ought to call this the solution. But for historical reasons, this is called the graph. That's its name. So the graph of the equation. So a big theme of what we're going to do for the rest of the semester is that we're going to look at equations, and we're going to categorize them and say, oh, it's this kind of equation or it's that kind of an equation in 2 variables. And some of the categorizations that we're going to use are going to be algebraic, in the sense that, oh, when we see this kind of thing, we want to do that kind of action, we'll perform these algebraic steps. But we're also going to look at it from the point of view of pictures, like, oh, I recognize that that kind of equation, and I know that its plot will look like that. It'll look like a parabola, or it'll look like whatever. Okay, so good. Final bit of mention is that very often, like on YouTube and what have you, people talk about math and what have you, and they'll refer to this picture as a graph, and that's not really correct, because the graph is the set, and then if you wanted to visualize, if you wanted to make a picture of the graph, that's called a plot. So this thing is called a plot. It's the same sort of distinction between the solution to this equation is that set. And that is a picture of that set. So this is a plot. So it's you know, some people might say that's like a distinction without a difference, but I promise that there is a distinction. And I feel it seems to me I need to say it because I'm gonna be using the words plot and graph according to those meanings, and it could be confusing if you hear me say graph and you're thinking picture, but I'm thinking set. Okay. So to that end, we're going to start with the simplest equation and graph that we can have, and those are going to be lines. So here we're going to try and say everything that can be said about lines. So, you know, by line I mean a line on the plane, and I mean that you know, it goes infinitely far in both directions, and it's flat. You know, it's not bendy. So this one is bendy. You know, it's bending. So this is not a line. So the first thing that we're going to do is we're going to make some categories for ourselves, and we're going to call these slope categories. So recall, so you know, remember the following: that every time that we draw a two-dimensional axis, that our convention is that if it's not explicitly indicated, then it's understood to be right-handed. So if ever we're going to draw a two-dimensional an axis like this and it's going to be left-handed, then you have to say something, because otherwise it's going to be understood to be right-handed. This is right-handed. And remember that the handedness can be visualized as a swirl. You can imagine that you're like stirring a cup of coffee in there, and the swirl is right-handed swirl is like this. The reason is because, you know, if you put your hand on the page with your thumb up, then that's the direction that your fingers go, right-handed. And the other convention is that so if you have a right-handed thing in a right-handed world, then that thing is reckoned as being positive. And if you have a left-handed thing in a right-handed world, that's reckoned as being negative. And so positive and negative just mean opposite of the world. Okay. So that being said, here we're going to draw four axes. So I can draw 4 different kinds of lines. Okay, so on this leftmost one, I'm going to draw a line that's going from top left-ish to bottom right-ish. So something like this. For this next one, I'm going to draw a line that's parallel to the horizontal axis. So that's supposed to be parallel. For the next one, I'm going to draw a line that goes from bottom left-ish to top right-ish. And then for the last one, I'm going to draw a line that's parallel to the vertical axis. Okay. Now, for each one of those lines, we're going to select 2 different points. So all that I mean by that is that you need to choose 2 points and you can't choose the same point twice. So maybe this one and this one, this one and this one, this one and this one, and this one and this one. So we got 4 lines. For each one of those 4 lines, we chose 2 points. So now what we're going to do is we're going to try and figure out, you know, in some sense, is that these lines, are they going what's going to be their handedness in some sense? So let's imagine that for this situation, we want to travel from one point to the other. But the way that we're going to do it is first we're going to do all of the horizontal motion, and then we're going to do all the vertical motion. So we're going to follow the first axis first, and then we're going to follow the second axis second. So like from here, we would travel to the right, and then from here we would travel down. So right down. But then you might say, why'd you start there? I wanted to start at the other one. Okay, that would be fine too. So we have to do all the horizontal motion first and then the vertical motion. So always follow the first axis and then the second axis. So from here we'd have to go left, and then from there we'd go up. Okay, so now if I just make a copy of that rectangle and pull it down here, then we could get out the ruler and we can measure it. It would have base and height. Maybe it would be like 3 by 5 or something. But notice that this rectangle has a swirl, a sense in which it's swirling. You can imagine, if you stirred your coffee like this, following a rectangle instead of like a normal person. But do you see that it would be swirling like this? So, is this rectangle a left-handed rectangle or a right-handed rectangle? Left-handed, because that's the direction that your left-hand fingers go. Okay, so that means that this is a left-handed situation in a right-handed world. So this is negative. So we're going to say that that concerning this line, its slope is going to be negative. Okay, now I'm going to jump over this one for a moment and look at this one. So again, you choose whichever point you want to start at, and then you move to the other point, and you first do the horizontal motion, then the vertical motion. So, blah, blah. And then you might say, oh, I didn't want to start at that one, I wanted to start at the other one. Okay. And then I can take that rectangle and transport it down here. And it would have its base times height. It would have its area. But do you see that it's swirling? So its swirl looks like this. Now, is that right-handed or left-handed? That's right-handed, because that's the direction your right hand fingers go, like this. So that means that this is a right-handed object in a right-handed world. So this is positive. Okay. Now the other two are curious. Imagine that if I could grab this red line here and I could wiggle it, and you'd notice the rectangle also wiggling to compensate. And if I take it and I start turning it, this red line, and start turning it so it's more nearly horizontal, then this rectangle would be getting shorter and shorter and shorter and shorter, right? It would start getting shorter. So what I want you to see is that either way, you could take this one and turn it to become horizontal, or turn this one and turn it to become horizontal. The result will be a rectangle that has 0 height. Okay, so it's like a trivialized rectangle. So, like that, and then you don't travel up or down, or like that, you don't travel up or down. That's kind of, trivialized. So, so as a result, this is like a rectangle that has no height. And if you have a rectangle that has height 0, what's its area? 0. So, you know, this is something to do with 0 somehow. But do you observe that that situation is also the same here? Is that this is also generates a rectangle that is trivialized in the sense that this is a rectangle whose base is 0. So these two have something to do with 0. And the convention is that we're going to say that this one is 0. And this one is undefined. So understand that that's what we're saying about the slope. So what I'm telling you is that this is what negative slope looks like. This is what 0 slope looks like. Positive slope, undefined slope. The reason for it has to do with the swirliness. You know, disagreement with the world, agreement with the world, negative and positive, and then you know, calling the you know, these both have 0 area, so you just have to make a choice. And the choice, the convention that everyone uses, they say this one is 0 and that one's undefined. Furthermore, on the matter of names, such a line right here is usually called a horizontal line, and this one vertical. Okay, so that's neat. That allows you to sort of qualitatively look at lines and say the slope is whichever one of those 4 categories. But we also want to be able to calculate and say, well, the slope is exactly thus. You know, I measure it and here's what it is. Okay, so here it is. So this is calculation. Slope. So here's the idea. So I'm just going to draw this sketch very quick. So here we have a system there, and suppose that we have a line like so. So now I didn't draw a scale, so and I didn't put measurements on it, so you can't tell me the exact value of the slope, but you can tell me which category it's in. Which category is it in? Negative. Definitely has negative slope. It's that kind. Fine. So now what I'm going to do is I'm going to select 3 points on the line, so 1, 2, and 3. And I'm going to do the same thing that we've done so many times. I'm gonna project these points down to the horizontal axis and project them over to the vertical axis and make right triangles. So I'll call this x1, x2, x3, and then now, because that's x1 and that corresponds to that point, I'm going to call that one y1. x1, y1, y2, y3. And what I would like for you to observe is that that's a right triangle, of course. And then inside of this bigger right triangle is a smaller right triangle. So that is a smaller right triangle that's in there. Notice that this angle right here, whatever it is, it's the same for the big one and the little one because it's literally the same angle. Now, that means that concerning these 2 triangles, we know that 2 angles are the same, right? They both have a right angle, and they both have exactly that angle, and that means that their third angles are also the same. So this angle right here has to be the same as this angle right here. So that's just, you know, a result from geometry. So what we have is we have a big right triangle and a little right triangle, and they're not the same as far as their lengths are concerned, but all the angles are the same. So we've got a situation that looks like this. We've got a big right triangle and a little right triangle. And so the fact that they have all the same angles, these two triangles are said to be some special word from geometry. Starts with S. That's all. That sounds like it. That's almost it. Getting further away. Starts with S. Ends with imilar. Similar. Yeah, that's it. It's similar. Okay. So similar. That's a trick. Similar triangles. So again, coming from geometry, when you have two triangles that are similar, that means that analogous ratios from the triangles have to be equivalent. So that means that if we take measurements of these triangles, we can construct ratios, and that has to be equal. So looking at the big one, so that's the big one right there. I can see its base will be x3 minus x1. So this measurement right here is x3 minus x1. What's the base of the little one? Yeah, it'd be x3 minus x2. Now, what's the height? And now I have to be a little bit careful here and say I'm actually talking about the signed height, because the height's actually going to end up being negative. It'd be the other way around. y3 minus y1. And that's going to be negative, right, because it's a small y minus a big y. So it's going to be negative. And this one will be y3 minus y2. So we took those measurements, and the following ratios must be equivalent. So equivalent ratios. That y3 minus y1 over x3 minus x1. That is to say, the big height divided by the big base must be the same as the little height divided by the little base. Those have to be the same. And understand that because the 3 points that we chose were arbitrary, that means that you can put those points anywhere that you wish. You could put this point way, a million miles down here, and the ratio still has to be the same. So summarizing, the picture looks like this: is that you have a line. You can choose any 2 points, and then you travel from one point to the other. So you travel like this, and then like this. We're going to refer to this distance as delta x, and this one as delta y. So delta x. So if this point is the point x1, y1, and this is the point x2, y2, then this would be x2 minus x1. This would be y2 minus y1. And the summary is that the slope is delta y divided by delta x. Okay, curious. So do we have time for a thing? Okay, so I have we have time. We have 30 seconds. What if we, very quickly, if I was to ask, here's two points. And we've got the line going through them. I could ask, what's the slope of this line? Well, notice that we could calculate it as follows. We could say, well, delta x should be 1, 2, 3, 4, 5. So delta x should be either positive 5 or negative 5. Which one should it be? It should be positive 5. But wait a second, if we did this one, and we started here instead of there, because there's no reason to start there, we could start here, we would go 1, 2, 3, 4, 5. So this one is saying that delta x should be what? Negative 5? Okay, wait a second. So if we use this delta x, then we would travel 1, 2, 3 down. So this would be saying delta y is what? Negative 3. But this one would be saying that it'd be positive 3. And why is this all working? Why is this all okay? Right. It's saying that the slope, you could look at it, the slope is delta y over delta x. So if you wanted to start here, then you'd be saying it's negative 3 over 5. But if you said, no, I want to start here, well, then it would be 3 over negative 5. So they're the same. All right, so that's all that we have for today. I hope you have a wonderful Wednesday.